what we're about to look at is kind of it's kind of like looking under the hood and seeing how the car works. Okay, this is now getting into the nuts and bolts of why limits do what they do. And as an extension to that, it turns out that limits end up being the underlying engine, for lack of a better analogy, that makes derivatives happen and makes integrals happen. So what I'm about to show you and get into is kind of the inner workings of all of it. So the precise definition of a limit. If you notice, we've been saying a lot of, oh, as x gets really close to a, those words really close or approaches or super close but not equal to, those are all very vague terms. And math people don't like vague terms, as you may be aware of. So what we need to do is we need a way of nailing this thing down in a more precise fashion. And that's what this is. Before we jump into that, I want to just have a simple discussion about absolute values. So if I give you a number line and I want the distance between 5 and 8, you're going to tell me the answer is what? Anybody? I'm not asking a hard question here. Distance between 5 and 8.
5.
Well, sorry, more than one person spoke at the same time. Try again. I heard 3. How'd you get that?
8 minus 5.
8 minus 5. Okay. Could you have done 5 minus 8?
No.
No. But watch. Are you watching? Watch this. Watch. Could you have done that?
Yes.
Yes. And you could have done this. So in general, the distance between x and a is absolute value of x minus a, or the absolute value of a minus x. Yeah? So from this day forth, absolute values with a minus sign between the two numbers inside gives you the distance between them. Okay? All right. Now, what if I write x minus 5, that distance is less than 2? What exactly does that mean? Okay, what's a possible number that I can plug in there to make it true? 6. Okay. I can put in 4 also though, right? Right?
Yes.
Okay, so this says distance between x and 5 is less than 2. In other words, 1, 2, there's 7. 1, 2, there's 3. We're talking about any number in this yellow region, not including 3 and not including 7, right? Cool?
Yes.
Okay. And so what we're about to do is we're going to talk about the distance between x and a has to be less than some, and I'm going to use a Greek letter, this is lowercase delta. Okay? So for this whole discussion we're about to jump into, we're going to have a lot of distances less than some value. Okay? And if I wanted to make a smaller neighborhood around 5, right? Maybe I just want the neighborhood to go from here to here in green, right? Then what would I do? I would write, instead of the distance between x and 5, instead of writing less than 2, I would put less than 1, right? And what if that would be for green? And then what if I want an even smaller distance in blue here, right? What if I just want that? between there. I would have to write something like the distance between x and 5 is less than a half. Okay? Could I say the distance between x and 5 is less than 0.0001? Sure, that would be, I can't zoom in that far. This is as far as it lets me zoom in. It would be a tiny little region like this, right? So if I've got this inequality, I can make a smaller and smaller neighborhood around a number by simply making this number closer and closer to 0, okay? All right, so now that we have that under our belt, so to speak, here's what we're gonna do. We know that the informal meaning of this thing, I'm gonna skip the thing above for time's sake. I may come back to it, we'll see. But the informal meaning of this is that we're trying to figure out what values f of x are approaching, right? F of x is getting really close to L, as x approaches A. Okay, well, let's look at the f of x approaching L business. What that means is the distance, right? If x is approaching L, we're saying the distance, which you now know is an absolute value with a difference there, between f of x and L can be made arbitrarily small. Okay? That's what it means to approach something, right? If you look at my little graph here, if I have an X inside yellow, and then I force it to be inside green, and then I force it to be inside blue, and then I force it to be inside red, wouldn't you say that point is approaching 5? Give me another thumbs up if that idea makes sense. Okay, so that's what we mean by making the distance arbitrarily small. So the way we're going to write this mathematically is, that is, for any, I'm going to use a lowercase epsilon, so it's that little e, for any epsilon greater than 0, no matter how small, what did I just write? Tell me in words what that says right here. What does that say? Use the D word.
The distance between fx and L.
Good. The distance between f of x and L is less than epsilon. Okay? In other words, no matter how small we make epsilon, right, as long as it's a positive value, just like we did over here, right, this is my epsilon. I can make it super small, positive. The smaller I make it, the closer x and 5 have to be to each other. So where this is going to happen for us is when we talk about approaching L. So if I gave you a graph that maybe looks like that, and we call this A, and we call that L, we have L plus a little bit right here. And when I say a little bit, I mean epsilon. And here I've got L minus a little bit. Okay? And f of x, let's say I have a point right there, f of x is going to have a y value inside there. So maybe that is my f of x. And so the idea is the distance between f of x and L is less than epsilon. If you look in here, the distance above and below, which I'm about to do in yellow, that distance above and that yellow distance below, those are both a distance of epsilon. So the way I've put f of x, it is now within what we call an epsilon neighborhood of L, meaning that its distance between f of x and L is less than this little positive number epsilon. Okay? I know it's a lot. I know it's a lot already, but we're going to play the same game now, but we're now going to do it on the horizontal axis. So if I give you the same graph, ish, it's not going to be perfect, and we put A here, and L say right there. This time we're going to get a little what we call delta neighborhood, A plus delta, A minus delta. And so for x to approach A means, I'm going to write much the same thing we have above. It means the distance between x and A can be made arbitrarily small. That is, we can say that the distance between x and A is less than some positive number delta, and we're also going to say greater than 0 because we don't want x to equal A. So I'll just put over here x cannot equal A because we might have a hole there. Now, what this is doing for us, if you imagine coming over here and picking an x value, which I'm going to do in red, within that little neighborhood around A, meaning that x, this is x right here, that x, the distance between x and A is less than delta, so that fits this thing. If I put that into my function, it's going to give me a value over here, right? And I can make my little neighborhood around L as small as I want. So let's start looking at this definition. If I choose, well here, let's back up a second. So we have f as a function that is defined on some open interval containing A, maybe not at A itself. We're letting L be a real number. This statement, right, our limit notation, means that for every positive epsilon, there exists a positive delta such that this is true. Now, again, this is brand new. This takes a little getting used to, okay? I want to start with this statement, okay? Does somebody want to chime in and use the distance word and tell me what this statement says?
The distance between fx and L is lesser than epsilon.
Excellent. So again, what he just said is the distance between f of x and L is less than epsilon. In other words, if I come back to this picture here and I choose epsilon to be this, I choose that distance, right? The distance, oh, I didn't do that very well. Hold on, let me move it a little closer. That's still not close enough there. I choose this highlighted green distance to be epsilon. Okay, so there's an epsilon above, and hold on, let me make it look a little more. And there's another epsilon below. Okay, so the distance there. and this guy is going to be f of x. Okay, so I choose a certain distance epsilon above and below L. I'm guaranteed if I take this now straight across, I'm guaranteed that no matter how small I make epsilon, and when I say that, think about maybe squeezing these in further, there and there. Imagine they're getting closer and closer to L. No matter how much I squeeze those in, as long as I have an f of x inside there, I'm guaranteed that x will be in this blue neighborhood here around, ooh, just made my x black, that blue neighborhood there around A. Okay, so I may give you guys a visual on this in a little bit, but the idea here is that we're zeroing in on the limit L by picking smaller and smaller epsilons. And what that does is it gives us new little regions down here in which everything in the blue region will give us an F value inside the little highlighted green region. Okay? And that's what this statement is saying. It's saying that as long as I pick an epsilon, I'm going to have a corresponding delta that any x I pick within delta distance of A, f of it will be within epsilon delta distance of L. I know, that's a lot. I'm going to bring up a visual real quick just to kind of hopefully nail this down a little better. Because usually at this point, half of the class is looking at me like I've lost my mind. So if you're nodding your head to yourself going, yep, I'm part of that group, you're not alone. As a matter of fact, the first time I saw this, I remember thinking, I don't like math anymore, and I like math. Let me open up a visual of this real quick. All right, so you should be able to see this graph on my screen. It's a simple graph for now, but the idea is this. If our x's are going to approach 2, so you can see 2 over there on the floor, and right now what it's saying is if I pick an x value in here, right, if I pick this point, say right there, and I plug it into the function, it's going to give me a value on the graph there, okay? And as we pick smaller epsilons, look at what's happening, right? When I say epsilon, I mean the distance above and below here. It's giving me a corresponding region on the floor so that any x I pick inside here, right, this j, I can move it around. But as long as I, you know what, let me do something to try to nail this a little bit better. All right, so these purple line segments I just created, and I'm hoping you guys can see this well enough. I know it's kind of small. They are giving me the intersection of J, which now is not moving. Come on, J, move. Oh, it won't go past there? That's stupid. Oh, well. Any J I pick in here, you can see that capital M is its Y value. And as I make my epsilon bigger or smaller, right, there's a really big epsilon, right? The distance between two, right now epsilon is 1, right? I'm 1 above 2 and 1 below 2. As long as I pick a J somewhere in here, and again, I don't understand why I can't get J to the other side there, but as long as I pick a J somewhere in this yellow or blue region, I'm going to have my M value within a distance of 1 from epsilon. As I make epsilon smaller, it turns out that my J is moving and it shouldn't. I guess the way I created it, it's no good. But anyway, the idea is that for each value that I pick inside my little epsilon neighborhood, I can find a corresponding neighborhood down below where j is, okay? So let's do one quick example. I will answer whatever questions you have. We'll do a little more with it next time. For those of you going, oh my gosh, this class just got totally out of hand and he's making no sense, don't freak out too much. Even though this is the stuff that's kind of underlying everything we do, we don't play with it that much in this class, okay? It's just a little bit here, and I'll mention it a couple other times. Here they want us to use the graph to find the number delta such that, and again, let's make sure we read this correctly, the distance between x and 3 is less than delta. So you'll notice 3 is here. They want us to find a distance delta going that way and a distance delta going that way. That guarantees that the distance between f of x and 2 is less than a half. Okay, so we've got this half here in green and a half there in green. Okay, so that takes care of this piece. Okay, that's what that's saying. And they're saying that they want us to find a delta so that no matter what red point I pick here, when I bring it across to here, it's going to give me an x value in the little region there. Okay? So, in other words, if I were to pick delta being 0.8. So here I've got a distance of 0.8. And here, if I subtract 0.8, it's going to take me over here to what? 2.2, right? And if I pick a point over here between 0 and 3.8, I'm in good shape. It's going to put my value in the green zone. But if I pick a point over here, it's not going to give me a value in the green zone. If I pick it over here, I'll be okay because this will give me a y value in that green zone also. So 3.8 is too big because that pink purple point isn't going to work for us. So I need something smaller than 0.8. If delta equals, well, what if I use 0.4? Now, if I may erase all these. What if I pick 0.4? Now my region goes from here to here. There's a 0.4 distance. And here it would go to 3.4 and I get a 0.4 distance. And now any point I pick in here, as long as it's in that region, will always give me a y value in the green region, right? Et cetera, et cetera. So that works. And if you're thinking, okay, that's good, he got an answer, good job, he messed it up the first time, but he got it this time. Would delta equal 0.3 work? Well, sure, it would just tighten it up even closer, right? Meaning I would end up going between 2.7 and 3.3, right? But 2.7 and 3.3 will still, no matter what value I pick, right? If I put 2.7 there and 3.3 there, any value in this little region is going to translate to a y value in the green region. Okay, so we can do any delta that's 0.4 or smaller. You could say delta is equal to this if you wanted to. That's a tiny little neighborhood. That's going to put it there, and we're going to end up with y values between there and there, but they'll still be in the green region. So that's what they're getting at with this problem when they're asking us to find, excuse me, find a delta that will work for that. that will satisfy that green inequality. All right.